Assalamu alaikum, sir. I'm Tasnia Naks, ID 20021113. So, our quiz 4 is actually on rectangular waveguide. So, for this rectangular waveguide, I have taken reference from YouTube videos and also the class note that sir has provided us. So, in rectangular waveguide, it is actually a hollow metallic tube with a rectangular cross-section area, where the rectangular waveguide confines electromagnetic wave that is traveling through it and guide the electromagnetic wave. And rectangular, similar to the parallel plate waveguide, rectangular waveguide supports two type of mode, that is TE and TM mode, transverse electric mode and transverse magnetic mode. And and also rectangular waveguide doesn't support transverse electromagnetic mode because when the wave travels longitudinally down the guide, the plane waves are reflected from wall to wall because the wall of the rectangular waveguide is made of metals. So, since there is internal reflection inside the waveguide, this process results in component of electric field and magnetic field in the direction of propagation. Rectangular waveguide are also often used in transmission lines. So, power flow is in the form of electric field and magnetic field only in the transmission line. There are some conditions that the wave propagate in the rectangular waveguide. Only if these conditions are satisfied, then the wave propagation happens. So the first point is that the cutoff frequency of the wavelength have to be greater than the operating wavelength, and cutoff wavelength have to be greater than the operating wavelength. That means the cutoff frequency have to be less than operating frequency because wavelength and frequency is inversely proportional. For rectangular waveguide, TE10 mode, 10 mode is dominant mode. Dominant mode that has actually the lowest cutoff frequency. So so here is a diagram, one type of diagram that we can see. Here it is actually a rectangular waveguide where it is one metallic plate and that is another metallic plate. So a wall of the electromagnetic waveguide is made of perfect conductor. As this is the perfect conductor, so there is internal reflections in when the light actually hits the wall, there is internal reflection. So what in this the plate, the conductivity of the plate, as this is metal, so the conductivity of the plate is infinity. We can say the length of the waveguide is L, and when a light actually passes through the waveguide, it passes by an angle. So the angle is denoted as theta angle. So if the angle passes to theta angle, there are two components of the light of the incident light, that is lambda p and lambda n. So lambda p is basically the parallel component, and lambda n is the normal component. This is the lambda n, and this is lambda p, that is the parallel component of the waveguide. From this we can say lambda n is equal to lambda by cos theta and lambda p is equal to lambda by sin theta. These are some of the light terminologies, light jargons, the incident light jargons. And the incident light actually falls traverse to this waveguide by a frequency, and the frequency is denoted by f equal to c by lambda. So here is the transverse magnetic mode in rectangular waveguide. If we actually explain transverse magnetic mode, it can be transverse electric mode can easily be derived. So to explain this, I will take the reference from the note that sir has provided us. So this is cross-section area of a rectangular waveguide. In our parallel plate waveguide, there is either B or either A, means we only have the width or length, but here or breadth. But here we have two components, that is B and A, means in X direction we have to calculate the size of the rectangle, and also in the Y direction we have to calculate the size of the rectangle. So for the transverse magnetic mode, in the transverse magnetic mode, when the wave propagates, the magnetic SZ component is basically zero. SZ component is basically zero because the magnetic field is transverse here, but EZ is not equal to zero. So if we see this slide, first to solve this, to get the all other field like Hx, Hy, Ex, Ey, we need to start from the Maxwell equation. So from the Maxwell equation, using the Maxwell equation, that the way we have derived from the parallel plate, the all Hx, Hy, Ex, Ey, all of the things can be derived, can be used for a rectangular waveguide as well. So we have to go till the general solutions of the waveguide, and then we'll put our updated Helmholtz equation, and plug updated Helmholtz equation to those general equation to find out the solution. So at first there is a four Maxwell equation. After the Maxwell equation, we perform the phasor form. In the phasor form, we actually gave that rho is equal to 0, z is equal to 0, j is equal to 0, because the charge because we are considering only free charges and current, ideal case. Then there is actually a general solution for guided EM wave, where we get this using the Carl equation. From this Carl equation from these two, Carl of E electric field and Carl of H magnetic field. After solving this, we get some solutions, and when you get some solutions, we substitute it in terms of Ex and Hy. Ex and in terms of electric field and magnetic field, in terms of transverse wave, means every equations have a transverse wave like Ez or Az or something like this. So we got here from four equations, that is this one, number 8, number 9, number 10. And from this thing, if we eliminate, we actually got other equations from 11 to 14. These are our main equations, where we have to plug in to get the value of hx, hy, ex, ey. We have to plug in the value ez here, because hz is equal to 0. So if we just go now to the rectangular plate waveguide, yes. So this picture and this picture is similar. We have to consider the same way, and the wave is actually propagating in the z direction. So previously in the paraplate waveguide, there is only one side. We are considering only one. It has only one side. There is a metallic plate constant condition, that is at x equal to 0 there is a metallic plane, or x equal to b there is a metallic plane, or y is equal to 0 there is a metallic plane, or y equal to b there is a metallic plane. But in x directions, that is actually not actually defined. So here in the rectangular waveguide, we are considering both the width and breadth of the rectangle. So for that, the solution of Helmholtz equation will change. Previously, the solution was only contained A and B, but here now it will contain C and D, because we are considering the two length. And if we solve the Helmholtz equation, we get this type of solution, that is Ez is equal to am sin kxx and so on. So here we can see there is actually a two boundary condition, that is from x equal to 0 and x equal to a, and another is y equal to 0 and y equal to b. So for all of this, why we are considering this boundary condition? Because at y equal to b there is a metallic plane, and y equal to 0 there is also a metallic plane, and at x equal to 0 this is a metallic plane, and x equal to a there is a metallic plane. That means, and we know in the metallic plane we have to consider the electric field is 0, because that is the conducting plane, and the conducting plane doesn't have an electric field. So as these portions are 0 here, we have to consider, we have to take all of this value, like at x equal to 0, x equal to a, y equal to 0, y equal to b. We have to derive the boundary conditions for, using this boundary condition, we have to derive a, b, c, and d value. So here, if we put x equal to 0, and here x equal to 0 is Ez is equal to 0, electric field is also 0. If we put this equation into this equation, Ez equation, we get a prime is equal to 0. And similarly, if you put y equal to 0, Ez equal to 0, we'll get c prime is equal to 0. This belongs to Ez equal to b cos sin x x sin ky y. And after that, if we give x equal to 1, Ez equal to 1, here we will get the kx value. And if we put y equal to b, Ez equal to 0, and we will get ky value from here. And here k is equal to kx and ky actually depends on the value of m and n. M and n means some integer value. So we'll go later on this m and k value. If we plug in this kx and ky value in the Ez equation, we get this Ez equation, that is b sin m pi by ax and sin n pi by by. And then if we plug this equation into our general solutions that we have derived earlier, that from 11 to 14 equation, if we plug this and if we keep the z is equal to 0, then we will get ex, ey, hz, xy. So this is the solution of rectangular waveguide, and then solution for the rectangular waveguide. Now here there is some of the mode of operation. What is the mode of operation? Mode of operation means, suppose if there is actually a if there is something, suppose if there is if you put n equal to 1.5 or n equal to 2.5 or n equal to 3.5, it will not reach to that mode. It only operates on the integer value of m and n. So the lowest mode of operation is when m is equal to 1 and n is equal to 1. So that is the lowest lowest order TM mode for the rectangular wave, then we can give a lot of combinations, like K in the KY we can give n is equal to 2, or in the KX we can give m is equal to 1. So from combining all of this, we can get a different type of mode of operation. And for the rectangular waveguide, there is actually some of the cutoff frequency, means below this cutoff frequency, no, if we pass any light sources to the waveguide, it will not propagate. So it have to, cutoff frequency have to, operating frequency have to be greater than the cutoff frequency that we have seen earlier. So if we derive fc is equal to, if we say fc is equal to 1 by 2 pi by 2 pi root over permittivity and permeability divided by m by a. M is basically the kx, m actually related to the kx, and n related to the ky, m by a square plus n by b square. And then if we get the lowest, if we want to operate in the TM1 mode, first order mode, then we have to maintain the lowest cutoff frequency. And if we want to go to the highest order, we have to highest mode, like second mode or third mode, operate in the TM third mode or fourth mode. So we have to also increase the cutoff frequency. If the, suppose if we want to operate in the fourth mode, so we have to make sure that our operating frequency have to be less than our operating frequency have to reach to the corresponding level, so that it can operate in the fourth mode. But like suppose if we apply FC or FCC1, that is the lowest cutoff frequency for the mode 1, to get to the highest order mode, will the order that mode will not actually that mode will not operate that time. We cannot actually function in that mode. So this is actually the diagram, like in FC11, the first mode, we get the first mode. In, if we increase the frequency, then we go 2 mode. If we increase the cutoff frequency more, we get 3 mode. So the actual sequence, this actually depends on B by A, that is B by A. And also there are some other parameters. Some other parameters are, this is the cutoff frequency. Then other parameters are propagation constant. Propagation constant is denoted by Bg. That is also depend on the cutoff frequency and the operating frequency, also the permittivity and permeability, and the wavelength lambda g. This is also depends on the cutoff frequency, and also there is a phase velocity that also depends on the cutoff frequency. So cutoff frequency to divide, and cutoff frequency actually depends on m and n value, that is the integers of the kx and ky. So similarly, we can find the TE waveguide. In the TE wave, we can see that there in the TE wave there is Ez is equal to 0. So we have to work with Ez. But in our parallel, in our metallic plane, the Ez, we do not have anywhere Ez is equal to 0. So we have to take the consideration of Ex and Ey. From the Maxwell equations that we know earlier, we have derived this Ex and Ey, where Hz has a value, and we will take the derivation of it, and then we get the Ex and Ey value, and then we will apply the boundary conditions. This is actually the same as a parallel plate waveguide. We will from the boundary conditions, and from that boundary condition we will get other values like Hx and Hy, and similarly we'll get the cutoff frequencies, also some of the dominant mode, if you see here. And here the cutoff frequency, here there is a cutoff frequency seen for the mode 1. So this is all about the rectangular waveguide. Thank you. Thank you.